Today we will be doing a quick review of exponents, roots, and polynomials. The laws of exponents only work when you are performing these operations with the exact same base. For example, if I'm multiplying a times a. It also works for number bases as well if this had been a 5 times 5. When you are multiplying the same base by itself, you add the exponents. When you are dividing the same base by itself, we subtract the exponents. When you have a power to another power, when you have an exponent being raised to an exponent, those two exponents can be multiplied. Anything in existence to the 0 power is a 1. And the last rule is that anything to the negative power is really out of place. It really belongs in the opposite position. Like, for example, this is in a numerator of a fraction, and it really belongs in the denominator. If you were to have a negative exponent already in the denominator, it's out of place, and it would be needed to be moved to the numerator. So let's take a look at some actual examples. So our first example has multiple rules going on. So we have to remember that when there's a power outside of the parentheses, it goes to everything inside of that parentheses. And then I must also remember that the large numbers, the coefficients, do not do the same thing as the exponents. The coefficients do normal things. They do not follow these shortcuts. So if I just had 2 squared, that means 2 times 2, which is 4. C has an understood 1 as an exponent, and 1 times 2 would give me c squared. And then D has 4 times 2, so d to the 8th power. Now that 4 did not come from me multiplying this 2 by the 2 outside. It just came from me happening to do 2 squared, which means this 2 times itself and happened to produce a 4. On the next parentheses, there's an understood 1 with both of these, so I'll distribute both the 5 to the 1 and the 1, and since it's power to a power, they get multiplied. So that is c to the 5th, d to the 5th. From here, I'm following the product rule. 4 times no other numbers. There's an understood 1 coefficient here, so 4 times 1 would just leave us with 4. But now that I'm doing c squared times c to the 5th, with the product rule, it says that I need to add the exponents, so that's c to the 7th. D to the 8th times d to the 5th would give me d to the 13th, and that would be my final answer because I couldn't combine any other terms. In our second example, you could technically simplify what's inside first and then distribute the 4, or you could distribute the 4, then simplify. I prefer to simplify first because I find that I make less mistakes that way. So if I simplify what's inside first, 5 and 20 are coefficients. I will not subtract them. They are just normal numbers, and 5 over 20 will reduce to 1/4. But when I get to these x divided by x's here, I'm going to follow the quotient rule. X to the 3rd on top with an x to the 1st on the bottom. 3 minus 2 will leave me x squared on top. Y to the 1st on top minus y to the 5th on the bottom would give us a y to the negative 4th power, but that's because there are more y's on the bottom than there are on top. So really, this y to the 4th power is just out of place. We should put our y to the positive 4th power on the bottom next to the 4. Keep in mind, all I did so far was reduce what's inside. There's still a 4 on the outside of the parentheses. Just like over here, when that exponent outside went to everything, this exponent has to go to everything in the numerator and everything in the denominator. So 1 is a coefficient, so I'm actually going to do 1 to the 4th power, happens to be 1. But then I have a power to a power, so that's that power rule here. 2 times 4 will give me x to the 8th power. Then on the bottom, 4 to the 4th power is 256. I'm not doing 4 times 4 because this big 4 here is a coefficient. When I get to the y though, since it's an exponent to another exponent, I can multiply and I get y to the 16th power. And that would be our final answer because I couldn't reduce, those are unlike terms, and 1 over 256, there's nothing else I can do with that. The last one here, I'm going to make sure I distribute this exponent to everything inside the parentheses. If it's an exponent, it'll get multiplied. If it's a coefficient, I'm actually going to do 2 to that power. So I have 2 to the negative 2 power, x to the negative 6 power, and y to the positive 6 power. Well, from here, the first two terms have a negative exponent, so it's not fully simplified. They are out of position. They are out of place. Right now, they're in an understood numerator with an understood 1 underneath, so both the 2 to the negative 2 and the x to the negative 6 need to be moved to the bottom. Y has a positive exponent already, so it should stay up top. So I've got y to the 6 still on top. Now on the bottom I have 2 to the positive 2 power and x to the positive 6 power. Because I have 2 here, I can actually compute 2 squared, so my final answer should be y to the 6 power over 4x to the 6 power, and that would be our final answer. The next thing to review is square roots. Technically, square roots can have two possible solutions, positive or negative. You can never take the square root of a negative number, though, because there is no such number in existence. It would produce an imaginary number. When we're taking the square root of a perfect square, it's pretty simple. You just compute it, and it is that number, like the square root of 81 is 9. But sometimes we're trying to take the square root of things that are not perfect squares, and we practice simplifying those to take out the largest perfect squares within there and leave whatever was left inside. So for example, square root of 216, I can think of 216 as 36 times 6. So I'm going to break down inside of here 36 times 6. And then k to the 4th came from k squared times k squared. So I broke this down into 36 and 6 because you can take the square root of this, but you cannot take the square root of this. So because I can take the square root of 36, I'm going to pull that out. Square root of 36 just happens to be 6. And then this 6 is left on the inside of the radical, inside of the square root. This one on the outside came from me taking the square root of 36. There just happened to be a factor of 6 left inside. I know that I had the right combination because 6 does not have any perfect squares hidden within it. The only factors are 6 and 1 and 3 and 2. When I take the square root of a variable, k to the 4th power, I have to think what was multiplied by itself to give me k to the 4th power. Well, that came from k squared times k squared. So the shortcut when we're taking the square root of variables to a power, we just have to divide this exponent by the little understood 2 here. So that would give me k squared on the outside. So our final answer would be 6k squared on the square root times the square root of 6. On our next example, 64 does happen to be a perfect square, so we don't have to guess what's hidden in it. I know square root of 64 is 8, so that's going to come out. But when I try to take the square root of m cubed, it's not an even number, so 3 is not evenly divisible by 2. So I have to think of m cubed as m squared times m to the 1st times n squared times n to the 1st. Because I can take the square root of m squared and n squared. Square root of m squared is just m. Square root of n squared is just n. But underneath the radical, we still had one m and one n left that we were not allowed to take out by using the square root. So what you can take the square root of comes out front, and what you cannot is left underneath the radical. Cube roots. In your graphing calculator, you get to cube root by hitting math 4, and that will pop up with the cube roots. So when you try to take the cube root of 250, it is not a perfect cube, so you'll get a decimal. So we have to see if there are any perfect cubes hidden within it. So perfect cubes are like 2 times 2 times 2, which produces 8, or 3 times 3 times 3, which produces 27. So when we try to find the perfect cube inside of 250, we find that it is the cube root of 125 times 2. So I can take the cube root of 125, that's just 5, that would come outside of the radical. I cannot take the cube root of 2, so that's going to be left underneath the radical. Same thing of when we were taking the square roots of variables, I simply need to be able to divide this exponent by the index here. 5 is not evenly divisible by 3, but I could break this x to the 5th power up into x cubed times x squared, because that's how I would get x to the 5th power. And I can take the cube root of x cubed, that would just be x. And then x squared would be left underneath the radical with the other two. Last example here, cube root of 56 isn't a perfect cube, but I know that 56 is divisible by 7 and 8, so I can think of this as 8 times 7. Cube root of 8 I can actually compute and take out would be 2. Cube root of 7 would have to stay under there because there are no perfect cubes hidden within 7. Since x and y both have exponents of 3, and 3 is divisible by 3, these are pretty simple. Cube root of x cubed is just x. Cube root of y cubed is just y. So that would be our final answer. Now if there are perfect squares or perfect cubes and there's nothing left inside, then simply compute it. If it says not to simplify, but instead it says round to the nearest tenth or hundredth, then you will just put cube root of 250 in your calculator and round to the nearest decimal that they specifically ask you to round to. Polynomials, we need to remember that if we are subtracting polynomials that we need to distribute the negative to everything in the second parentheses. We also need to remember that combining like terms only happens when you have the exact same variable to the exact same power. So I'd have 3x squared minus 5x squared. We only change the coefficient. That would give me negative 2x cubed. I'm sorry, I think I said squared. And then we have 3x squared minus minus, that's going to make that plus. So 3x squared plus 7x squared gives us plus 10x squared. Then we have a negative distributed to this positive 6x. That's the only x to the first power. That's going to stay the same, negative 6x to the first power. And then we have 9 minus negative 9. So when I distribute this negative, that makes that plus as well. So 9 plus 9 will leave us with a plus 18 at the end. There's no other like terms. It's in standard form. That would be our final answer. Multiplying polynomials, you could draw your Punnett squares or you could use the distributive property. You just need to make sure that both terms in the first parentheses goes to both terms in the second parentheses. So 2x times 4x would give us 8x squared. 2x times negative 9y would give us negative 18xy. Y times 4x would give us plus 4xy, and y times negative 9y would give us negative 9y squared. From here, our two like terms are the xy's, so we would have 8xy minus 14xy minus 9y squared. Couldn't put anything else together. So the final thing would be dividing polynomials. What you're going to try and do here is basically see if you can factor any of the trinomials and see if there's a common factor to cancel out with anything else. Right now I can't just like cancel out these m's and anything like that. I have to put this in standard form on top and see if it's even factorable. So standard form would be 2m squared plus 3m minus 4 all over m plus 5. Well, I need to see if I can factor what's on top, because if one of its factors is m plus 5, then they'll cancel. If it's not, then I couldn't simplify it any further. So I'll use slip and slide. That's when we took the 2 and multiplied it by the negative 4, and we got m squared plus 3m minus 8. And we thought of the factors of negative 8 that would have a difference of 3. So things that multiply to give me negative 8 are 2 and 4 and 1 and 8. And so even if I switch the negatives, the difference between 4 and 2 is not 3, and the difference between 1 and 8 is not 3. Therefore, I couldn't go any further. The top is not factorable, so I don't have any common factors that would cancel out, and this is simplified all the way. Now, in the event that you could go further, for example, if I had something like m plus 3 times m minus 4 all being divided by m minus 4, if you could have factored it and it had a common factor, then you would be able to cancel that out and your final answer would have just been m plus 3. But that's only if you can go further. So from here, you will be working on your next packet, and we will have that quiz this Thursday.